Have you ever wondered how your GPS just knows the fastest route in seconds? Or how a social media app figures out exactly who you might know? Well, the secret behind all of that is the powerful world of data structures and algorithms. And in this quick review, we're going to break down everything you absolutely need to know for Units 3 and 4.
Look, if you're staring at a page full of nodes and edges and you're trying to figure out the difference between pre-order and post-order traversal, trust me, you are not alone. These concepts can feel really tricky at first, but honestly, they're all built on just a few simple, logical ideas.
So, in the next few minutes, we're going to clear up all that confusion and give you a really solid roadmap. By the end of this, you'll be able to walk into your exam feeling confident you can absolutely ace it. Ready to get started? Okay, let's dive right in.
So, first things first, why do we even need to bother with complicated things like trees and graphs? Well, think about a simple array. It's great for a basic to-do list, right? But what happens when you need to represent something way more complex, like a family tree or all the connections on a social network? Yeah, a simple line of data just won't cut it.
You know, imagine trying to find one name in a phone book with millions of entries just by starting at A and reading every single name. That's a linear search. It's incredibly slow. But what if you could organize that data to jump straight to the S section? That's the whole point of nonlinear structures. They let us map out these complex relationships and search through them with amazing speed.
All right, let's talk about our first big nonlinear structure, the tree. The easiest way to think about it is a company's organizational chart. You've got the CEO at the very top, then managers who report to the CEO, and then employees who report to those managers. It's a classic parent-child relationship, and that's a perfect job for a tree. Okay, so a tree is basically a bunch of nodes, and the edges connecting them, but it has two really important rules. First, there's only one starting point, and we call that the root. And second, there are absolutely no cycles. You can't start at one node, follow a path, and somehow end up back where you started. Oh, and here's a little trick for your exam. A tree with n nodes will always have exactly n1 edges. It's that simple. Now, to really get trees, you gotta know the lingo. The node at the very top, that's the root. Any node that has other nodes connected below it is a parent, and those nodes underneath it are, you guessed it, its children. And finally, any node at the very end with no children is called a leaf. So how do we actually visit every single node in a tree? This is called traversal. What's cool here is how the rule completely changes the output. For in order, you go left, then visit the root, then go right. For pre-order, it's root left-right, so you visit the main node first before exploring its branches. And for post-order, it's left-right root, meaning you visit all the children before you visit the parent. The order is everything. Now, let's talk about the real star of the show, the binary search tree, or BST. It's got one simple, beautiful rule that makes it incredibly fast. For any node, everything to its left is smaller and everything to its right is larger. This is just like a dictionary. This simple rule lets you find what you're looking for extremely quickly by always knowing which way to go.
So trees are fantastic for hierarchies, but they do have one big limitation. A child can only have one parent. What if you want to represent a more complex network, where anything can connect to anything else? For that, we need to talk about graphs.
A graph is really just a collection of vertices, which is just another word for nodes, and the edges that connect them. The single biggest difference from a tree is that graphs can have cycles. Think about a round-trip flight. You can fly from New York to LA and then fly right back. That's a cycle, and it's something you will never, ever see in a tree.
So how do we actually represent a graph in our code? Well, there are two main ways. The adjacency matrix is a big grid showing every possible connection. It works, but it can use up a lot of space, so it's best for dense graphs where almost everything is connected. On the other hand, the adjacency list just lists the neighbors for each node. It's way more efficient for sparse graphs, like a social network. And just like trees, we need ways to traverse graphs. First up is breadth-first search, or BFS. It explores level by level, kind of like ripples in a pond. This makes it perfect for finding the shortest path. Then you have depth-first search, or DFS. It dives as deep as it can down one single path before it comes back. So here's the key. Use BFS for shortest path problems, and use DFS when you need to explore every single possibility, like solving a maze. Okay, so we've got all this data stored in these awesome structures. But what good is it if we can't find what we're looking for? Or if we need to put it all in order? That's where searching and sorting come into play.
When it comes to searching, you basically have two choices. You've got linear search, which just checks every single item one by one until it finds what it's looking for. It works, but it's slow. Then you have binary search. It's way smarter. It keeps dividing the search area in half, making it incredibly fast. But, and this is a big but, it only works if the list is already sorted.
And that brings us to sorting algorithms. The simple ones, like bubble sort, are easy to understand, but they are painfully slow for big lists. Then you have the heavy hitters, merge sort and quick sort. These are the pros. They use a clever divide and conquer strategy that makes them way faster. For large data sets, these are almost always your best bet.
So binary search is fast, but what if you need to be even faster? Like, what if you want to pull an item from your database instantly in just one step? For that kind of speed, we need hashing.
So how does this magic work? It's pretty simple, actually. First, you start with a unique key, like a student ID number. Second, you feed that key into a special hash function. Third, that function spits out a number. And that number is the exact index in an array where your data lives. It's direct access. The only thing to watch out for is a collision. That's when two keys get the same index, but we have clever ways to handle that.
And these exact same ideas apply to how we organize files on a computer. A sequential file is like a diary. You have to read it from the beginning. An indexed file is like a phone book. The index helps you jump to the right section much faster. And a hashed file? That's like a gym locker. Your ID tells you the exact location for instant access.
And there you have it. We've covered a ton of ground really fast. But before we wrap up, let's just quickly lock in the absolute most important things you need to remember for your exam.
Okay, here's your final cheat sheet. Remember, trees are for hierarchies. Graphs are for networks. Binary search is super fast, but only on sorted data. Quicksort and merge sort are your go-tos for big lists. Hashing gives you practically instant lookup. And file structures just apply all these ideas to storing data on a disk.
So as you're studying, think about this. Which of these powerful data structures is the engine running behind your favorite app? When you connect these concepts to the real world, they really start to stick. You've got this. Now go crush that exam. Good luck.